In the previous class, we were studying, we started force method and I basically made a brief introduction about that method. So we will continue from the point from where we left. I will just review briefly that in the force method, the main idea was to correlate. For example, if we have an indeterminate beam, then the main purpose of this method was to figure out the reactions of this beam. Since we cannot use the equation of equilibrium or equation of equilibrium are not sufficient to find out the reaction of this kind of a beam. So we have to rely or find out some other method to find these reactions. And for that purpose, we would write the compatibility equation. Now, what is compatibility equation? These equations basically correlate the deflection with the reaction. For example, if at this point I will remove this force and apply a reaction force Vy, then it will produce some kind of a deflection in this beam. And I will correlate these deflections with this reaction. And since we know the procedures to find out these deflections, and we will write the correlation equation, find out this deflection, and then figure out this reaction. Once we have this reaction, we can easily find out the other two reactions, and this beam will be determined. Actually, it will remain indeterminate, but we can solve it to find out these unknown reactions or forces. So, in the previous lecture, is the voice quality clear, and can you see the screen properly? Can someone confirm this?
Sir, the screen is visible, but the voice is breaking.
दानिया की आवाज बहुत दूर से आ रही है, दोबारा बोलो।
सर, आपकी आवाज टूट रही है, स्क्रीन नजर आ रही है।
आवाज टूट रही है।
हल्की हल्की ब्रेक्स आ रहे हैं आपकी आवाज में।
Okay, let's just continue for 5 or 10 minutes, and if the problem is not resolved, then we can look for some other solution.
Sir, your voice is better now.
What?
Your voice is clearer than it was before. It's all right now.
Okay, it's fine. Okay, in the last lecture, we basically took one pole. For example, we had this beam, and in this reaction, we removed this particular support. That was the roller support. You can remove any support you want. So, in the case of roller support, you will have a vertical reaction over here. But it is quite possible that in some question, it may ask you to take the moment as redundant. So in that case, how what will be our compatibility equation? Today we will start our lecture with this one. For example, now if we want to take the moment as redundant, let's say we have this beam, which is an indeterminate beam, and we want to find out all these unknown reactions. And this is a load, any random load. Just like in the last lecture we did, we will call this as actual beam, and we have to divide this into a primary beam and a redundant beam, or a beam on which a redundant is applied. So in this one, we will take the moment at this point as redundant and make this a determinate structure. So when we remove this fixed support or take the moment as redundant, we will have one unknown reaction at this point and one unknown reaction at the right support. So this will be basically our primary structure, since we have removed the moment, and now we can use the equation of equilibrium to find out the reaction in this one. I will basically write over here. And the fourth structure and the third structure will be the one in which we will apply this redundant movement. Here the load will remain as it is, and in this one the load will be removed, and we will apply the redundant movement that we have removed, and we will have this shape. Now, by using the principle of superposition, again we can write the we can write the compatibility equation. Now, look at this primary structure again. In this one, the deflected shape of the beam will be something like this one, and at this end we will have rotation that is theta a. Now in this one we have applied this MA. There is no load P over here because we have to satisfy the uh, principle of superposition, or in simple words we should say that the sum of these two forces or these two beams should be equal to this one. For example, if I add these two beams, what will happen basically? Here the moment is acting, and over at this point the hinge support is there. So they will add up and it will give me the fixed support. And when we write the compatibility equation, we will make these two deflections or rotations as equal, and they will cancel out, and the overall effect is that the rotation at this point will still remain zero. But we will use this superposition principle to write the compatibility equation, and using that we can find out one particular reaction. So this is the whole idea. So coming back to this beam, when we apply this redundant movement, we will have the rotation at this point, and we will represent it just like in the case of deflection, we represented it by delta dash AA. So in case of movement, we will represent it by theta dash A A. And if I want to write this, just put it as redundant movement applied. This is our third beam. So now let's write our compatibility equation. So if I look at my original structure or actual beam, there is no deflection at this particular point. So I will write 0, and in this beam we have this rotation theta A due to this applied load. So I will write this as theta A, and in this third beam I have this rotation theta dash AA due to this moment MA. So I will write over here theta dash AA. And in the last lecture we also studied one formula for the flexibility, that was deflection is equal to F into load. And this F is the flexibility, this P is the applied load, and this deflection is obviously the deflection at any particular point. So if I want to change it with rotation, because rotation is also one form of deformation in the structure, so that will be theta is equal to this F will be now angular flexibility. Actually, both of these are same. In the case of linear deflection, it is represented by F. In the case of angular deflection, we will represent it by alpha, and this P factor will be, now since we are applying this moment, so it will be moment, or basically moment is also a type of a load, so we will just replace it with moment, and these two will produce this reflection, that is theta A and this alpha A. So I can replace this theta dash A with this factor over here. 0 is equal to theta A plus alpha A dot moment at point A. Now this is our compatibility equation. We have this particular beam, and in this beam we can find this theta A by applying any of the deflection or rotation calculation method, double integration method, conjugate beam method, or virtual work method, or even the Castigliano's theorem. We can apply those methods and figure out this rotation theta A, and from this beam we can figure out this moment A. Oh, sorry, this moment A is unknown, and from this beam we will calculate this alpha A. What is alpha A? Last time I told you about the flexibility. So the flexibility was basically from this equation we can see that the flexibility is deformation when a unit load is acting. So similarly, this angular flexibility is the rotation in the structure when a unit movement is applied. For example, we have this beam, and if this is the unit load that is acting, then the deflection that is being produced in this beam will be equal to flexibility. And in the case of angular flexibility, it will be rotation when unit movement is being applied on this beam. Then this rotation will be the angular flexibility, or it will be equal to angular flexibility in for the case when unit load is any kind of unit load is applied. So we will apply the unit load, and we will calculate this deflection, and this deflection will be equal to our flexibility. And once you have this rotation, this flexibility, you can use this equation to find out this moment ma. Now once you have this moment ma, then what will be your beam? It will be something like this one. You have this moment ma, and now this beam is determinate. We have this unknown, let's call it as va, and this unknown vb, and you will simply use the equation of equilibrium to find out these two reactions. So this is how you write the compatibility equations for deflection or for rotation. So is there any question about this one?
सर
Yes.
सर हमने कैंटिलीवर की जगह फिक्स सपोर्ट क्यों लगाया है?
कैंटिलीवर की जगह क्या लगाया है?
सॉरी, कैंटिलीवर के जगह हिंज सपोर्ट क्यों लगाया है जब हम इसको ब्रेक डाउन किए?
कि हमने इस बीम को स्प्लिट किया है टू पार्ट्स में. अब लेट सपोज ये हमारे पास एक्चुअल बीम है. इसको पहले हमने प्राइमरी स्ट्रक्चर बनाया जिसमें हमने कैंटिलीवर सपोर्ट रिमूव करके हिंज लगाई. बेसिकली हमने इसके अंदर से एक मूवमेंट वाला रिएक्शन रिमूव कर दिया कि हमें वो कैलकुलेट ना करना पड़े. ठीक है, फर्स्ट पार्ट में ये किया है, और दूसरे पार्ट में वो मूवमेंट हम वापस ले आए हैं. तो बेसिकली इन दोनों का जो सम है वो दोबारा इक्वल टू दिस एक्चुअल बीम बन जाता है. तो अब हम इन दोनों बीम्स को यूज करके एक ऐसी इक्वेशन बनाना चाह रहे हैं कि जिसके थ्रू हम ये मूवमेंट पहले से ही फाइंड कर लें और हमें इस बीम की तरफ ना जाना पड़े. तो फिर हमने इन दोनों को यूज करके एक इक्वेशन लिखी है, और इस इक्वेशन को हमने डिफ्लेक्शन से रिलेट कर दिया है, और उन डिफ्लेक्शन को यूज करते हुए हम ये अननोन रिएक्शन फाइंड कर लेंगे. हमने रिमूव नहीं किया, हमने जस्ट स्प्लिट किया इस बीम को टू पार्ट्स में.
नहीं
एक्सक्यूज मी सर.
यस.
सर अल्फा एक दफा दोबारा समझा देंगे अल्फा क्या चीज़ थी?
अल्फा, आपको फ्लेक्सिबिलिटी की समझ आ गई है? फ्लेक्सिबिलिटी क्या थी?
नहीं सर.
फ्लेक्सिबिलिटी, इस इक्वेशन को देखो, दैट इज डेल्टा इज इक्वल टू एफ टी. अब इस इक्वेशन में फ्लेक्सिबिलिटी क्या है? फ्लेक्सिबिलिटी इज बेसिकली लोड डिफ्लेक्शन डिफ्लेक्शन पर यूनिट लोड, राइट? इसी
सर
तरह इस इक्वेशन को देखो, इसमें अल्फा है. अल्फा इज वी कॉल इट एज एंगुलर फ्लेक्सिबिलिटी, और ये क्या है? रोटेशन पर यूनिट मूवमेंट. ठीक है, अब इसको फिजिकल मतलब क्या है इस चीज का? मतलब अगर आपके पास एक बीम है जिसपे अगर आप यूनिट लोड लगाओ, तो जो डिफ्लेक्शन प्रोड्यूस होगी, फ्लेक्सिबिलिटी की डेफिनेशन क्या है? डिफ्लेक्शन पर यूनिट लोड. ठीक है,
यस.
तो जो आपके पास डिफ्लेक्शन प्रोड्यूस होगी, दैट इज लेट्स कॉल इट एज डेल्टा, इट विल बी इक्वल टू दिस फ्लेक्सिबिलिटी एफ. ठीक है, और इसी तरह एंगुलर फ्लेक्सिबिलिटी क्या है कि जब आप ये मूवमेंट लगाओगे यूनिट, तो जो आपके पास रोटेशन प्रोड्यूस होगी, रोटेशन कैसे फाइंड करते थे? उस पॉइंट पे टेंजेंट बनाते थे, और टेंजेंट के साथ जो एंगल होता है, तो
यस
दैट
सर.
विल बी इक्वल टू एंगुलर फ्लेक्सिबिलिटी. ठीक है,
ठीक.
मतलब आपके पास एक बीम है, उस पर यूनिट लोड लग रहा है, और आपने ये डिफ्लेक्शन फाइंड करनी है, और ये आपकी फ्लेक्सिबिलिटी होगी. ठीक है, और अब ये डिफ्लेक्शन आप कैसे फाइंड कर सकते हो? कोई भी मेथड यूज कर लो, डबल इंटीग्रेशन मेथड्स
यस.
पढ़े थे.
बस थैंक यू सर.
अच्छा, लेट्स सॉल्व वन एग्जांपल, तो ये चीजें हमें क्लियर हो जाएंगी. Okay, so we have this beam. Or is, the purpose is that we have to analyze this beam and plot the shear force and bending moment diagram. EI is constant, and in this question they have basically asked us that the we are supposed to take the redundant at B support. Actually, in some of the question it will be specified. In other question, it is up to you that which support you want to take it as redundant. So let's solve this one and find the reaction. So we have this beam on which a load of 50 kilonewton is acting. This distance is 6 meters. And we have to find out the reaction. Again, we will split this beam into two beams. This is our primary structure, and since we are supposed to take the redundant at B support, this is A, this is B. So we will remove this roller support. Sorry, this is our actual structure. This fixed support will
Sir,
remain as it is. Yes.
sir, how do we know कि हम कब redundant force apply करें या redundant moment?
एक्चुअली इट इज अप टू यू, लेकिन इस क्वेश्चन में हमें बताया हुआ है कि रिडंडेंट बी सपोर्ट पे लेना है या बी पॉइंट पे लेना है, तो बी पॉइंट पे रोलर सपोर्ट है, तो वी आर सपोज टू अप्लाई द वर्टिकल फोर्स, राइट. So we have this 50 kilonewton external load that is acting on this one. This is our primary structure plus. Now we will apply the redundant force. Let's call this as VB or VY, and we will remove this external load. Now the important thing is that you don't have to worry about the sign or the direction of this one. For example, you can also apply this reaction in the downward direction, and later on when you will get the answer, you will see that if it is negative, then your assumed direction is wrong, and you can just change the direction. So you can take any direction for these applied load. Uh, in the case of reaction, it is usually in the upper direction, but it is not a fixed thing. But in the case of movement, usually things get confusing. So just apply the movement in any particular direction if you are taking that as redundant. And later, the signs of final answer will tell you that whether your assumed direction was correct or not. And if it is negative, just change the direction and the answer will remain same. And the answer will be, जो भी answer होगा, that will be your correct answer. Anyway, so when we apply this 50 kilonewton force, what will happen? It will produce some kind of deflection in this beam. And due to this By, the deflection will be produced. Since we have applied it in the upward direction, so it will deflect in the upward direction. So this deflection, let's call this as delta V, and this deflection as delta dash V V. Okay, so we have these two deflections, and now let's write the compatibility equation. So what will be, we also did it in the last lecture. So in the initial beam, we have zero deflection. And in this primary structure, we have this deflection delta B. And in this structure, when we have applied the redundant force, we have deflection delta dash BB. But you can see that these two deflections are in the opposite direction. So we have to take negative sign with one of these deflection. So let's assume that the downward deflection is negative. So I will have the negative sign with this deflection delta B. So you have this compatibility equation. Now we can replace this delta dash BB again with, or I will write it over here, minus delta B plus FBB flexibility at point B multiply by By. So this is our equation. We just need to find out this delta B, this FBB, and we will have this By reaction. Now, one way to find these two unknown is to do the whole thing, that is double integration method, or everything as a whole. Or the other thing, or the simple thing, obviously, is if you have this book. In this book, there are these formulations that are already given for different types of beam for deflection and rotation. You can directly use these formulas and you can find out these deflections. So you don't have to repeat all those steps. It is given in each edition of this Hibbeler book. So you can take help from this one.
Excuse me,
Okay.
sir.
Yeah.
Sir, for example, we use these formulas for mistake. What if quizzes वगैरह में would be allowed to bring these formula sheets as well, या फिर वो खुद ही करना पड़ेगा arrange?
If it is in the quiz, I can give you the formula for that particular beam which is in the quiz. But again, I'm telling you that I will give you one problem in this lecture. There is one assignment problem. You have to, or you should revise at least one method. You should know one method where you can apply that and calculate the deflection, because sometimes maybe these formulas won't work, because these are like for 5 or 6 cases. What about if there is something different than these beams? Then you should know some method to calculate this deflection. At least
अच्छा,
review method.
yes sir. और दूसरा, say, could you share this with us if it's possible with you?
It is in the book. You have Hibbeler.
हाँ, yes sir.
So inside front cover there is this formula.
चल ठीक हो गया. Thank you sir.
Okay. So for cantilever beam, if this is a beam and there is a load that is acting at end of this beam, and also you should be very careful while using this formula. There are some confusions. I will tell you just one. In this case, we have deflection as PL cube over 3EI and rotation that is equal to PL square over 2EI. Now these two formulas are for maximum deflection and maximum rotation. And in the case of cantilever beam, usually the deflection and rotation are maximum under the point load, or at the point where load is acting directly. So in our case, for example, in this one, you can see that load is basically acting at central point, and we need to find out deflection delta B, which is directly at the extreme end, right? So we will slightly modify this. Now this deflection or theta maximum is basically the deflection at this point, but this point is under the point load. So these deflections and rotation are basically under the point load. So in our case, the load is acting at the center, for example, over here, okay? And the deflection at center is, or I can say deflection at C point, let's call this point as C. Deflection at C point is PL cube over 3EI, And similarly, rotation at point C is PL square over 2EI, right? So if I write down delta B, so can anyone tell me how can I correlate this particular rotation at point C, that is delta C, with this delta B? Can anyone tell me the equation for this delta C? Sorry, delta B in terms of delta C.
मल्टीप्लाई बाय 2 होगी
सिमिलर
सर
ट्रायंगल से करेंगे.
What will be the equation? Tell me the equation. Just write on your pages. You know this. You have already done this. This is delta B. This is load of 50 kilonewton. This is delta C. And if I plot a tangent,
So it's half of delta B.
half of delta B. Where is the tangent? At this point somewhere. And since it is almost a straight line, so let's say that this angle is theta C, right? So this is theta C, this is delta C. What will be delta B? Can I say that this distance is delta C, and what will be this length? What will be this length? Anyone? This length is 6 feet. Plus, if this is 6, this is theta C. Can I say that this is 6
सर
theta C?
6
Think about it now. So
Yes, you
this
can, sir.
delta V is delta C plus 6 theta C. Now we have this value of delta C, that is PLQ over 3EI plus 6, and theta C is what? PL square over 2EI, right? This P is 50. Just substitute the values. Length is 6 feet or 6 meters, I guess. Yeah. Now just be careful about this one. This length is, we have to substitute the half length. If the load was acting at extreme right, and then we could have used the full length. But since the load is at the center, so we will use the half length for this one. 3, and this EI factor is constant, plus 6 into again 50 cross 6 here divided by 3 into EI. So what is this answer in terms of EI for this deflection at B point?
So 9,000 over EI.
Yes. Actually, over here it's 2
Sir,
EI.
14,400 over EI नहीं आ रहा.
There is a mistake. Over here it is 2 EI. Because in this formula of rotation, if you see, this vector is 2. So this deflection will be 9,000 over EI kilonewton meter cube. Right? So everyone got this answer, I hope. So now we have this deflection delta B, and we just need to find out this FBB. So this flexibility is basically is also the deflection, but in the case when the load is unit load. So we will use the same formulation, and for example, we have this beam. This is the, let's suppose that this is the unit load, and we need to find out this deflection. So from this beam, we can see that the deflection will be PLQ over 3EI, and this deflection is equal to FBB. So what is P in this case? P is 1. Length is, since the load is acting at the extreme right end, so the length will be 12. This 3 will remain as it is, and this EI will is a constant, so it will be with this one. So what is FBB?
Five 76 over EI.
ये हारून आप बता रहे हो ना,
जी सर.
बुक से देख के बता रहे हो?
नहीं सर, कैलकुलेट करके बता रहा हूँ.
तो ये पीछे वाला आपने सही कैसे बताया था? ये तो मैंने इक्वेशन ही गलत लिखी.
सर मैं देख रहा था इस वजह से.
So this is FBB, ठीक है. And now we have both these factors, delta B, FB, and only unknown is this BY, which is the reaction. So we will substitute these value into this one, and we will directly get the values of this unknown reaction. So 0 is equal to minus 9,000 over EI plus 576 over EI, that is this flexibility, multiplied by BY. So now can you give me this
सर
reaction
हम ये
BY?
फ्लेक्सिबिलिटी को हम लोग डायरेक्टली डिफ्लेक्शन के बराबर इसलिए ये यूनिट लोड की वजह से ले रहे हैं.
Yes. देखिए flexibility की equation क्या है? Delta is equal to FP. So flexibility is basically equal to deflection when the load is unit load, that is 1. अगर load 1 है तो it is equal to deflection. So हमने क्या किया, हमने उसी बीम पे unit load लगाया है और उसके accordingly हमने deflection calculate की है और वो deflection हमारी flexibility.
Okay.
So what is BY? Arun. Can you hear me now?
सर 15.63.
Yes. So this reaction is 15.63 kilonewton. Okay. So now we have this beam on which this reaction is 15.63. This is BA. This is MA. And this load is 50 kilonewton. This distance is 6 meter. And this distance 6 meter. So can you find out this VA and MA now? Zia, VA की क्या वैल्यू होगी? Anyone? Can you give me the value of VA?
34.7.
34.37.
In which direction? Upward or downward?
Upward, sir.
34.7. And what is this moment? Which direction? Clockwise or counterclockwise? This one? Sorry, clockwise. This is counterclockwise. 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 It will be in counterclockwise direction. Just check your cross check.
Counterclockwise.
So now we have all these reaction, and the final step was to plot the bending moment diagram. And since you have everything, so what will be bending moment diagram look like? So at this point we have this 112 kilonewton. One 12.4. At center, it will pass on something like this one, and this bending moment diagram will close over here. And what is this value at center? Anyone? Plus
187.56.
how much?
187.56. So 187.6.
1
187.6. Yes, sir.
187.6. Anyone else?
$95 RS.
95.
Huh?
And at the end, it will. This is your bending moment diagram. Now if you see this question, इसमें हमने क्या सिर्फ एक डिफरेंस आया है या एक हमने नई चीज की है, दैट इज दिस कंपैटिबिलिटी इक्वेशन. उसके अलावा सारी चीजें हम लोगों ने पहले पढ़ी हुई हैं. दिस डिफ्लेक्शन मेथड एंड दिस बेंडिंग मोमेंट डायग्राम और कैलकुलेशन ऑफ these unknown forces. So if you can figure out or if you can write this compatibility equation correctly, then these questions are not difficult. It is same like the equilibrium equation. जैसे आप वो equation of equilibrium लिखते थे reaction find करने के लिए, इस केस में आप एक compatibility equation लिखते हो to find out this deflection और उनको आपने correlate किया हुआ है unknown से, तो you have one reaction. और जब आपके पास एक reaction आ जाएगा तो उसके बाद सेम स्टेप्स हैं कि आपने बाकी दो रिएक्शंस फाइंड कर लेने इक्वेशन ऑफ इक्विलिब्रियम से और फिर शीयर फोर्स एंड बेंडिंग मोमेंट डायग्राम फाइंड कर लेनी है. और अगर ये डायग्राम क्लोज हो रही है तो मतलब आपका क्वेश्चन ठीक है, अगर क्लोज नहीं हो रही तो यू आर मेकिंग अ मिस्टेक समवेयर. तो दिस इज अ काइंड ऑफ अ चेक. तो एक्चुअली इस कोर्स में आई विल बी गिविंग यू सम असाइनमेंट प्रॉब्लम. सो इट्स बेटर के यू डोंट हैव टू सबमिट इट राइट नाउ, सो जस्ट कीप डूइंग इट. अभी हमने बीम्स कर रहे हैं, इसके बाद फ्रेम्स करने हैं, फिर ट्रसेस करने हैं. जब ये पूरा फोर्स मेथड कंप्लीट हो जाएगा तो कंबाइन इन सब असाइनमेंट प्रॉब्लम को आप सबमिट कर सकते हो. तो अभी आपके लिए बीम्स से रिलेटेड प्रॉब्लम है, सो इट्स बेटर कि आप ये प्रॉब्लम साथ साथ करते रहो. So it will make you, it will help you to understand these concepts in a better way. So you have this assignment problem, लेकिन इसमें एक डिफरेंस है. सेम प्रॉब्लम है, आपने मूवमेंट को रिडंडेंट लेना है एट ए सपोर्ट, तो हमने उसकी कंपैटिबिलिटी इक्वेशन भी लिखी है, तो यू कैन सॉल्व दिस क्वेश्चन. लेकिन डिफ्लेक्शन के लिए एक तो आप वो इक्वेशन यूज कर सकते हो डायरेक्टली, but in this assignment problem you have to apply some methods जो कि हमने पहले पढ़े हैं to figure out the deflection. और इसका पर्पस ये है कि आपके वो मेथड्स दोबारा से रिवाइज हो जाए. मतलब जो थीटा ए होगा कंपैटिबिलिटी इक्वेशन में, वो आप डायरेक्टली फार्मूलाज यूज करके नहीं लिखोगे. आप कोई भी मेथड यूज कर लो, मोमेंट एरिया मेथड लगा लो, वर्चुअल वर्क मेथड से आप फिगर आउट कर लोगे जो भी आपके पास अननोन रोटेशन हैं या डिफ्लेक्शन या वट एवर इज द केस. तो आपने डिफ्लेक्शन उन मेथड से फाइंड करनी है और मूवमेंट को रिडंडेंट लेना है. सो दिस इज प्रॉब्लम नंबर 1 एंड दिस इज प्रॉब्लम नंबर 2. actually it is similar to this one, but in this one there are no values, so you will get the answers in terms of p and length. So this is your assignment problem number 2.
सर ये सबमिट
So-
कब तक कराना है?
You don't have to submit it right now, but जब हमारा ये फोर्स मेथड कंप्लीट हो जाएगा ट्रसेस और फ्रेम्स, उसके बाद उनकी भी प्रॉब्लम्स होंगी, तो वो इकट्ठी आपने सबमिट करानी है.
ऑल राइट
लेकिन
सर, थैंक
बेटर कि ये
Yes,
आप साथ साथ करते रहो,
यस सर.
क्योंकि ये इसी से रेलिवेंट है जो हमने पढ़ ली है. So any question about this one? So if there is no question, then we can move on to next one. अच्छा, अभी तक हमने जितनी बीम्स की हैं, all of them had degree of indeterminacy equal to 1. अब फॉर एग्जांपल आपके पास एक बीम है, let's suppose this one, and there is this load P1, there is this load P2 that is acting on this beam. ठीक है, so you have this beam, let's call this as, so what is the degree of indeterminacy in this one? कितने unknowns हैं? Plus, how many unknowns do you have in this beam?
5.
5 सर.
Okay, 5. Actually horizontal अगर load नहीं है तो we don't consider it. तो ठीक है 5. So how many equations?
सर अगर हॉरिजॉन्टल लोड नहीं फिर तो वन इक्वेशन होनी चाहिए ना, फिर मतलब वर्टिकल इक्वेशन होनी चाहिए. सो
फिर भी 2 equations होनी चाहिए ना. Movement की भी तो equation.
अच्छा हाँ
Anyways,
ठीक है,
आप
दो इक्वेशन
तीनों
होंगे सर.
equations consider करें, don't get confused. So 5 minus 3. So we have 2. Degree of indeterminacy for this beam is 2, that is greater than 1. So जो पहले हमने दोनों problems या even in the theoretical part we discussed was the beam with 1 degree of indeterminacy. So we wrote the compatibility equation for one beam. But in this case, there are two unknowns, or there are the degree of indeterminacy is 2. So we should have at least two compatibility equations so that we can figure out the unknown reactions or we can solve this beam. So उसके लिए there is a small change in this method. Actually, not a small change, the method still remains the same. So the method to write the equation of compatibility slightly changes. So let's just follow the same procedure. This is our actual structure or actual beam, and let's just split it into two parts.
क्लास कितनी निकली सर?
Can you please turn off your mic? So let's suppose we will take these support B or the reaction at B and C as redundant. So what will we do in the primary structure, just like we used to do in previous problem? We will remove these two reaction that is at B point, this one is at C point, and other two reactions will remain same. So these loads will act on this beam as it is, and this beam will deflect something like this, and the deflection at this particular point is delta B. At this particular point, the deflection is delta T, right? So now you have these two reactions and these two deflections, and this is our primary structure. And the third one will be, again, like we used to do in the previous cases, we will apply
सर
the
हम कोई भी सपोर्ट हटा सकते हैं ना, जरूरी तो नहीं है कि हम
yes
बी और
any support. So in the third case, again we will apply these redundant reactions back onto this beam, and we will remove the external load. So then we will have at point B a redundant reaction, let's call it as By. Now again, like I told you, we can apply in this direction or in the downward direction, whatever direction is. It doesn't matter. The final sign will dictate that what is the actual direction. So it depends on you. So this is the redundant reaction at point B or at support B, and this is the redundant reaction at point C or support C. So again, due to these reactions, the beam will deflect something like this. And now the deflection, or what do we call it? That is delta dash, or we will apply these in separate beams. Let's just wait. So let's call this deflection as delta dash BB, and this is our point B, and this one is C. And in the case when we apply this is point C. Now in the third case, we will apply the redundant at C. Let's call this as Cy. And due to this Cy reaction or Cy force, we will have this deflection at this point delta dash Cc. Okay. Now there is another thing. when this force By is acting at this B support, it will also produce the reaction, some kind of a deflection at this particular support. Now we will call that is C point. We will call this deflection at point C as delta dash CB. Now this notation means that this is the deflection at point C due to this load at point B. Now what is the purpose of considering this reaction, this particular deflection? Why are we not considering this deflection or this deflection or this deflection? Now there are two reasons for that. First, when we'll be writing the equation, we need to find, actually our main purpose is to figure out the force that is acting at this particular point C, because we need to equate this force to the reaction that is acting at point C. For example, we can consider the deflection at this particular point, that is, let's call this point is F. We can also consider this reaction, but there is no physical meaning or there is no purpose of finding out this particular reaction. Let's call it, if it is Fy, there is no purpose of finding this reaction because we don't need it. We are considering only this deflection so that we can correlate this with the external reaction and find out directly the reaction. For example, this delta Cb directly uh, directly is directly related to this particular reaction Cy. You will see when we will write the equation. Is directly related to this Cy, and this Cy is what we need in this question. We obviously we can find out all the deflection or we can consider it, but there is no purpose of doing that. We will just make our calculation more complex. So we have to consider only those reactions or only those deflections at deflection at those points on which we are removing the support, so that we can find out the reaction Cy or By or whatever is unknown. So in this case, when this Cy is acting, there is also this particular deflection at this point, and we will call this as deflection. Let's call this as deflection at point B due to load that is acting on point C. This is basically deflection BC. Now this deflection delta dash BB will be equal to what? Can anyone tell me? How can I correlate it with this BY? Again, use this same relation class. So this delta BB will be FBB multiplied by what is load, that is BY. Okay. And what is this delta CC? That is again equal to FCC multiplied by applied load is CY. So this is the deflection at point C. Okay. And what is this delta CB? Can anyone tell me the equation for this delta CB?
Sir, F CB into BY.
That is FCB, and the applied load is BY in this case. So it will be BY. And this delta dash BC will again be FBC, which is the flexibility at point B due to load that is acting at point C, multiplied by, since the load that is acting on this beam is CY, so that will be CY. Now, since we have two unknowns, one is this CY and the other one is this BY, so we need to have two compatibility equations. And now we can easily write two compatibility equations for each deflection. For example, for point B and for point C, we can write two equations separately. So for point B, we can write the equation as, initially in this one at point B, there is no deflection, so that will be equal to 0. In this primary structure, we have deflection as delta B. In this structure where we have removed this redundant, we have this deflection, that is FBB into By, and in this third one where we have applied this load Cy, we have this deflection, that is FBC into Cy, right? And similarly for point C, in the initial structure, the deflection was 0. In this primary structure, we have this deflection as delta C. In this one, we have this deflection as FCB into By. And in this one, we have the deflection as FCC into Cy. I'll come on to this point that how we can figure out this one, but obviously this can be correlated with the deflection. Now look into these two beams.
Excuse me, sir.
Yes.
Excuse me, sir. Sir,
Yes.
मैंने पूछना था कि FBC और FCB सेम चीज़ नहीं होगी क्या?
Yes, it will be the same thing, but I will explain it later. Just ignore it for now. So,
all right, sir. Thank you.
In this equation, if you see that this delta B is the deflection at point B, this delta C is reflection. Again, this is deflection, these four values. So we can figure out these four terms or these six terms, and we have two equations, and in these two equations we have two unknowns, that is By and Cy. And if we solve these equations simultaneously, we can figure out this By and Cy. So now you know the method that when your degree of indeterminacy is greater than 1, then how to write your compatibility equation and how to find out the reaction. Now, for example, if you have another beam like this one, on which let's suppose there are or degree of indeterminacy is 3. Now for this beam, can you write the equation of compatibility? How many equations will we have? Anyone?
Three.
Three,
We will
sir.
have
Two,
three.
sir.
We have these three extra
Three.
reactions. So we will have 3 equations just like this one, and in each equation there will be one extra term and 3 unknowns, and we can write those equations, and when we solve those equations simultaneously, we can get the reaction. So now you know that no matter how much is the degree of indeterminacy, you can write the equation of compatibility and you can solve these questions directly. And you just need to find out the corresponding deflections, right? So, Alyan, you were saying that these two deflections will be equal. How come? Can you give me some reason or some mathematical reason, or can you prove it?
सर वैसे आई डोंट नो आपसे जो आपने जो डिफ्लेक्शन डायग्राम्स भी बनाई हैं उसमें भी एक तरह से मतलब इट डज शो कि मतलब दे कैन एंड एट द सेम प्लेस एट द सेम पॉइंट बिकॉज इन दीज केसेस द फोर्स इज एट द सेंटर तो द डिफ्लेक्शन एट बोथ पॉइंट्स बोथ हाफ्स
बात कर रही हो ना, देखो आप केस स्पेसिफिक बात कर रहे हो कि इसमें आपको लग रहा है कि इधर मैंने लगाया है या इधर लगाया। कोई मैथमेटिकल प्रूफ हो ना, कि कंक्रीट प्रूफ हो के उसको कोई नेगेट नहीं कर सकता। I was telling you in last lecture also that this FBB, अगर हम इसका इंटीग्रल लें या इसको मेथड ऑफ वर्चुअल वर्क लेट सपोज उससे सॉल्व करें, तो वो क्या था, मूवमेंट स्क्वायर ओवर EI into dx, राइट? तो बेसिकली ये फ्लेक्सिबिलिटी होती क्या है कि लोड और डिफ्लेक्शन व्हेन द यूनिट लोड इज एक्टिंग, ठीक है? तो अब हमने लेट सपोज ये फ्लेक्सिबिलिटी फाइंड करनी है एफ, दिस इज लेट्स कॉल दिस एज पॉइंट ए, लेट्स कॉल दिस पॉइंट एज बी, ठीक है? तो एफ बी ए, दिस इज एफ बी ए, अगर मैंने ये कैलकुलेट करनी है तो मुझे क्या चाहिए? ये फ्लेक्सिबिलिटी होती है कि अगर आपके पास यूनिट लोड एक्ट कर रहा हो तो इस पॉइंट की फ्लेक्सिबिलिटी एफ ए है और इस पॉइंट की फ्लेक्सिबिलिटी अगेन एफ बी है। तो इसका पर्पस क्या है कि आपके पास ए पॉइंट पे यूनिट लोड एक्ट कर रहा है और आप मूवमेंट की इक्वेशन ए पॉइंट पे यूनिट लोड एक्ट कर रहा है और आप डिफ्लेक्शन फाइंड कर लो, तो आपके पास वो डिफ्लेक्शन इज इक्वल टू फ्लेक्सिबिलिटी बी ए है, ठीक है? अगर हम लेट सपोज मैं इसको मेथड ऑफ वर्चुअल वर्क से सॉल्व करना चाहता हूँ। मेथड ऑफ वर्चुअल वर्क क्या था, उसकी अगर मैं इक्वेशन लिखूँ डिफ्लेक्शन की, तो वो थी कैपिटल एम स्मॉल एम इंटू ई आई डी एक्स। अब ये कैपिटल एम क्या था कि मूवमेंट व्हेन एक्सटर्नल लोड्स आर एक्टिंग, और ये स्मॉल एम क्या था, मूवमेंट व्हेन यूनिट लोड इज एक्टिंग वर्चुअल वर्क मेथड में। ठीक है, अब लुक एट दिस पर्टिकुलर बीम। अब फ्लेक्सिबिलिटी तो होती ही वो डिफ्लेक्शन है जिसमें एक्सटर्नल लोड इज यूनिट लोड। तो मतलब आपके पास जो कैपिटल एम है उसकी इक्वेशन, लेट्स कॉल दिस एज व्हेन द लोड इज एक्टिंग एट पॉइंट ए, तो इसकी इक्वेशन कोई भी रैंडम 2x+3 और वट एवर इक्वेशन आ जाएगी। ठीक है, तो ये कैपिटल एम आ गया आपके पास, दैट इज इक्वल टू एम ए। और उसके बाद स्मॉल एम, या स्मॉल एम की इक्वेशन क्या होती है, या वो कैसे लिखते हो आप, कि आप पॉइंट बी पे या जिस पॉइंट पे आपको डिफ्लेक्शन फाइंड करनी है उसके ऊपर फिर एक यूनिट लोड लगाते हो। ठीक है, और फिर इस यूनिट लोड के लिए आप एक मोमेंट की इक्वेशन लिख लेते हो। लेट्स कॉल दिस मोमेंट इक्वेशन एज एम बी, इसको भी हम यही कहते हैं 2x+3 है। ठीक है, तो फ्लेक्सिबिलिटी आपके पास बी ए क्या हुई, दैट विल बी इक्वल टू एम बी इंटू एम ए ओवर ई आई डी एक्स। ठीक है, इस बारे में कोई कंफ्यूजन की, ये फ्लेक्सिबिलिटी इसकी समझ आ गई है ना, ये मैंने कैसे लिखी है। मतलब वर्चुअल वर्क मेथड में पहले आप एक्सटर्नल लोड लग रहा होता था उसके अकॉर्डिंग आप कैपिटल एम की इक्वेशन लिख लेते थे, फिर आप यूनिट लोड लगाते थे उस पॉइंट पे जिस पॉइंट पे आपको डिफ्लेक्शन चाहिए। ठीक है, वो यूनिट लोड हमने ये 1 लगाया इस पॉइंट पे, और इसके अकॉर्डिंग हमने मूवमेंट की इक्वेशन लिख लिया और वो दोनों इसमें सब्सटीट्यूट की, तो ये इक्वेशन हमारे पास बन गई है फ्लेक्सिबिलिटी की, या दिस इज आल्सो डिफ्लेक्शन, और ये डिफ्लेक्शन फ्लेक्सिबिलिटी के इक्वल है। राइट, एनी कंफ्यूजन अबाउट दिस वन?
नहीं सर।
अच्छा, अब आते हैं कि ये दोनों इक्वल कैसे हैं, एफ ए बी और एफ बी ए। अब ये तो हमने एफ बी ए फाइंड कर लिया, अगर हमने एफ ए बी फाइंड करना हो तो उस केस में क्या होगा कि आपके पास ये सेम बीम है। ठीक है, ये पॉइंट ए है, दिस इज पॉइंट बी। अब एफ ए बी फाइंड करना है। ए बी का मतलब है कि आपके पास जो इनिशियल एक्सटर्नल लोड है 1 का, वो पॉइंट बी पे लग रहा है, और उसकी वजह से जो इधर फ्लेक्सिबिलिटी प्रोड्यूस हो रही है दैट इज एफ ए बी। ठीक है, तो लेट्स कॉल दिस, ये दोनों बीम सेम है, तो इसके लिए जो मैं मूवमेंट की इक्वेशन लिखूंगा वो फिर क्या आएगी, 2x+3, क्योंकि ये सेम बात है कि इधर भी बी पॉइंट पे लोड लग रहा था, इधर भी बी पॉइंट पे लोड लग रहा है, तो दिस विल बी माई मूवमेंट इक्वेशन। ठीक है, और सेकंड स्टेप में क्या करते हैं कि जिस पॉइंट पे हमने फ्लेक्सिबिलिटी या डिफ्लेक्शन कैलकुलेट करनी है उस पॉइंट पे हम यूनिट लोड लगाते हैं। ठीक है, इस पॉइंट पे हमने फाइंड करनी है, तो इस केस में इक्वेशन क्या होगी, दैट इज इक्वल टू ये जो हमने एम ए की इक्वेशन लिखी है, तो वो सेम इक्वेशन होगी। अब इसके लिए जब मैं फ्लेक्सिबिलिटी को लिखूंगा, अब ये इस केस में कैपिटल एम है, ये इस केस में स्मॉल एम है। ठीक है, अब जब मैं एफ ए बी की डिफ्लेक्शन इक्वेशन लिखूंगा, तो दैट विल बी एम बी, बिकॉज कैपिटल एम इज एम बी, मल्टीप्लाई बाय एम ए डिवाइडेड बाय ई आई इंटू डी एक्स। ठीक है, अब ये दोनों इक्वेशन देखें, इधर आपको लिखना चाहिए था एम ए एम बी। अब ये दोनों इक्वेशन सेम है या नहीं?
यस सर है।
दीज टू इक्वेशंस आर सेम। ठीक है, तो इसका क्या मतलब हुआ कि deflection at point B due to load at point A, that is at BA, is equal to flexibility at point A due to load at point B. ठीक है, मतलब ये दोनों फ्लेक्सिबिलिटी सेम होती हैं, एंड दिस पर्टिकुलर लॉ और दिस पर्टिकुलर कॉन्सेप्ट इज नोन एज Maxwell concept of Maxwell's theorem of reciprocal displacement. Just give me one ठीक है। सो दिस पर्टिकुलर मेथड और ये जो कॉन्सेप्ट है कि ये दोनों फ्लेक्सिबिलिटीज इक्वल हैं, दिस इज नोन एज मैक्सवेल थ्योरम ऑफ रेसिप्रोकल डिस्प्लेसमेंट। और उसने क्या कहा था कि डिस्प्लेसमेंट ऑफ पॉइंट बी ऑन अ स्ट्रक्चर ड्यू टू यूनिट लोड एट पॉइंट ए इज इक्वल टू डिस्प्लेसमेंट ऑफ पॉइंट ए व्हेन यूनिट लोड इज। और ये हमने इधर मैथमेटिकली प्रूव भी कर लिया है कि ये क्यों इक्वल है। अब क्योंकि लीनियर फ्लेक्सिबिलिटीज इक्वल हैं, तो सेम प्रिंसिपल की बेस पे हम कह सकते हैं कि जो एंगुलर फ्लेक्सिबिलिटीज आएंगी इन केस ऑफ मूवमेंट, वो दोनों भी इक्वली होंगी। और आप उसी को इसी मेथड की बेस पे वो भी प्रूव कर सकते हैं कि वो कैसे इक्वल होंगे, राइट। सो एनी क्वेश्चन अबाउट दिस वन?
तो इसमें स्पोर्ट्स टाइप उसमें
आपकी
वो
आपकी आवाज ठीक, माइक थोड़ा दूर रख।
सर इसमें अगर सपोर्ट्स हमारे डिफरेंट पोजीशंस पे हों तो वो इस चीज़ को वो करेगा।
सपोर्ट्स डिफरेंट पोजीशन पे मतलब कैसे?
यानी कि सर अगर जैसे फर्स्ट करें वो ये जो एज एन ये भी अभी जो दोनों एंड साइड्स है ना, लाइक एक्सट्रीम साइड्स हैं, अगर इनमें से कोई रोलर सपोर्ट हम थोड़ा सा लेफ्ट साइड पे कर लें ताकि हमारे बीम थोड़ी सी ओवर हैंगिंग हो जाए।
ठीक है, ऐसे हो जाए।
जी सर।
नहीं, फिर भी कोई डिफरेंस नहीं पड़ेगा, इट विल रिमेन द सेम, क्योंकि काम तो आपने एक ही करना है ना। लेट सपोज इसकी डिफ्लेक्शन यूं हो जाती है, ठीक है, ये ए पॉइंट है और आपने ये फ्लेक्सिबिलिटी फाइंड करनी है, ये बी पॉइंट है, ठीक है, दैट इज एफ बी ए। तो बात तो वही है ना कि आप पहले यहाँ पे एक्सटर्नल लोड लगाओगे और एक मूवमेंट की इक्वेशन लिखोगे, फिर यहाँ पे यूनिट लोड लगाओगे और मूवमेंट की इक्वेशन लिखोगे। और दूसरे केस में भी आपको क्या करना पड़ेगा, इन्वर्स काम करना पड़ेगा, इधर आप लगाओगे और बाद में इधर लगाओगे, तो वो एक ही बात है। तो सपोर्ट से कोई वो फर्क नहीं पड़ेगा।
सही।
So any other question? So if there is no question, we can conclude this lecture over here. हमने एक प्रॉब्लम करनी थी, लेकिन I think it's better that we do it in the next class. So this is it from today's lecture, and try to solve those assignment problems by yourself. And जो जब तक आप वो सॉल्व नहीं करेंगे तो नहीं आपका ये कॉन्सेप्ट बनेगा। और द प्रॉब्लम इज कि हमारा इस दफ़ा कोर्स कंटेंट ज़्यादा है, सो हमारे पास इतना टाइम नहीं होगा कि हम ज़्यादा प्रॉब्लम क्लास में प्रैक्टिस कर सकें। फॉर एग्जांपल अभी बीम की हमने एक प्रॉब्लम प्रैक्टिस की है, तो यू हैव टू प्रॉब्लम फॉर योर सेल्फ, ट्राई टू प्रैक्टिस दोस, एंड इफ यू फेस एनी डिफिकल्टी just let me know and we can discuss it. So if there is no question, this is it from today's class, and we'll meet on Thursday again inshallah. Till then, Allah Hafiz.